So today we are going to be analyzing motion that is defined parametrically. So we are going to be looking at one problem, breaking it down, we're going to graph it parametrically, and then we'll take a little closer look and take a look and see if we can analyze a little bit more as has to do with motion. So here we go. A particle moves so that its position measured in feet at any time t seconds, for t between 0 and 3 inclusive, is given by x of t equals 2t minus 1, y of t equals t squared minus 1. Okay, so part A, complete the table below. So for t values, already given to you from 0 to 3 because that's what we're told. Now you could always plug in any value for t, not just 0, 1, 2, and 3, as long as the number that you're plugging in is between 0 and 3. So you could plug in 1/2, you can plug in 2.7, but just to simplify what we have right now, we're just going to go up in integer values. So let's start with x, and we're just going to plug t equals 0 in. So 2 times 0 minus 1, that's equal to negative 1. Plug in 0 into the y equation, we have 0 squared minus 1, that's negative 1. Do the same thing for t equals 1, so we have 2 times 1 minus 1. We have 1 squared minus 1, t equals 2. 2 times 2 minus 1, 2 squared minus 1. And then when t equals 3, 2 times 3 minus 1, 3 squared minus 1. Okay, so now that we have the table complete, now we can go on to the next step, which is to sketch the graph of the path using the points that we just found. Check your graph using a graphing calculator. Your graph should be a smooth curve. All right, so plugging in negative 1, negative 1, 1, 0, 3, 3, 5, 8. Okay, and then you want to draw this as much as curved as you can. And then let's go ahead and not forget, for parametric equations, we also are told the direction of the graph. So when t equals 0, we're at negative 1 at the bottom point there. And then we are moving towards t equals 3, which is 5, 8. So we'll just draw in those arrows to indicate the direction. Now, if you were to check this on your graphing calculator, you would want to make sure that your mode is in parametric mode. Okay, so under mode, you'll see you can put it in function mode, polar mode, and then I think it says par, which means parametric. And you just want to make sure you're in parametric mode. That way, when you are in that mode and you go to your y equals, you'll be able to plug in x equals and y equals. And then you'll want to set your t value to be between 0 and 3. But your graph should look the same as we have here. All right, so let's continue. Part C, on your graph, in addition to the smooth curve, draw in line segments connecting consecutive points. Okay, so from t equals 0 to t equals 1, we'll draw in a straight line there, a line segment. And then from t equals 1 to t equals 2, another one there. And from t equals 2 to t equals 3, another line segment there. Now it should look pretty close to the curves, but not exactly, because these are straight lines and not exactly the same as the curved line. Now for the next part here, it says algebraically calculate the length of each line segment. So how do we do that? Well, let's say you're looking at that first line segment there, going from negative 1 to 1, 0. If you were trying to calculate the length of that line, you can think of it as using the Pythagorean theorem, right, to figure out what that length would be. So let's go ahead and do that for each line segment. So I'm going to call this first line segment C, C1. Okay. So this is 2 squared plus 1 squared, take the square root, that's the square root of 5. Okay. C2 would be 2 squared plus 3 squared, take the square root of that, that would be the square root of 13. And the last one, C3, is 2 squared plus 5 squared. So that's 25 plus 4, 29 squared of 29 feet. So we've calculated the length of each blue line that I've drawn in there. So this is different from calculating the actual length of the curve, right? This is just the line segments between the points. Now, even though this is not exact, it's pretty close to that pink curve, right? So let's go ahead and approximate the distance that's traveled by the particle that moves on the path by adding up all those line segments. Okay, so that's square root of 5 plus square root of 13 plus square root of 29. And just so that we can actually add them together, we are approximating, right? That word approximating means you can round, you can use decimals. So this should come out to be about 11.23 feet. Now, let's analyze this. Do you think that your approximation is too large or too small? Explain your reasoning. Okay, so we came up with an approximation 11.23 feet. Now, how do we know if it's too large or too small? Well, take a look at the picture that we have here, right? The pink curve is the actual distance that the particle's traveling, whereas the blue lines are approximations, but they're just the slightest bit shorter, right? It's the straight line distance from one point to the next, whereas the pink curve, it curves, right? It goes around a little bit more, goes around, it's more apparent probably in that first segment, but that pink line is definitely longer. Okay, so since the line segments appear to be shorter than the actual curve, the approximation is too small. All right, next part. The speed of the particle can be calculated as distance divided by time. What is the particle's approximate average speed over the time interval, 0, 3? Be sure to state units. Okay, so we know that we're approximating, so we're going to use that distance traveled that we just found. And we know speed is distance divided by time. So the time interval is from 0 to 3, which is a total of 3 seconds. So this is going to be 11.23 feet over 3 seconds. So that comes out to be about 3.74 feet per second. Okay, next part. Write a rectangular equation for y in terms of x. All right, so this is transforming a parametric equation into a rectangular equation. Remember, the steps in general are to take one equation, get t by itself, and then substitute into the other equation and simplify. Okay, so it looks like the first one would be easier. So let's go ahead and solve for t in the first equation. So x plus 1 equals 2t, divide both sides by 2. Okay, and now let's substitute into the second equation. So we have y equals x plus 1 over 2 squared minus 1. So now we have just one equation, just in terms of x and y. We eliminated the parameter. All right. If you want to simplify this, you can, but there's no need in this particular case. All right, part I. Find the domain and range for the function that you found in part H. Remember that the domain and range are determined so that the graph will be the same as it is in parametric form. Okay, so really we're just going to look at the graph that we have and look and see, well, if we're trying to write the domain and range for the function that we just wrote down, we have to restrict it to being between certain x values and certain y values. So look at the graph that we came up with. What was the domain restriction? Well, it went from -1 all the way to 5, including those two values. So that's the domain. And the range, now you're looking at the y values, and the range would be from -1 all the way up to 8, including those two values. Okay, so it is important to note that when you are changing from one to the other, right, in parametric form, you have very clearly, okay, t is limited to being between 0 and 3, but then when you change it into rectangular form, when it's just in terms of x and y, because the parameter goes away, there's no way for us to restrict it in terms of the parameter. So we have to restrict it in terms of the domain and range. Okay, that's all we have for today.